Okay. So at the last part of the previous lecture, we learned about the logistic regression. Its name is regression, but it actually does binary classification. Okay. So its output is some value between 0 and 1. The logistic regressor, it outputs some floating value whose range is from 0 to 1. Okay. And for that value, we will threshold it. Some output Z would be in between this range. And if Z is larger than 0.5 or larger than or equal to 0.5, we will finally output the 1. Okay. And if the Z is smaller than 0.5, we will finally output 0. Okay. By thresholding the Z value, we will do actually binary classification, right? In binary classification, the outputs consist of 0 and 1, right? Meaning class 1 and class 0, right? So anyway, by seeing this probability, by thresholding this final output value of this logistic regressor, we will do binary classification, okay? And when we use, this is actually the sigmoid function, right? If x, their values are like this, sorry. If the formula is like this, their x and y graph looks like this, right? So x is from -infinity to infinity, and y, but the y is bounded to 0 to 1 value, right? So if you insert some signals to the sigmoid function, okay, actually this is, we call this as sigmoid function like this, right? If we input some value to this sigmoid function, then the output values are bounded between 0 and 1, okay? And this is some linear operation, right? Multiplying some weight to the input and adding some bias, okay? Actually, this would be implemented in Torch.nn linear layer, right? Doing multiplying some weight and adding some bias. We are wanting to transform the input signal by this linear operation, right? Okay. Anyway, if we input the x, and if after transforming this input signal by linear operation, we will input it again to the sigmoid function to obtain this floating values that is between 0 and 1, right? And we want to threshold it by 0.5 and want to get this kind of discrete integer, meaning the binary class, okay? That's the binary classification, okay? And I also explained this, right? And I already told these two are same, right? And this yn means ground truth for each sample, right? So for each x, it will have its corresponding labels. And this, in binary classification, this should be belonging to 0 and 1, right? And some floating signals x is there, right? And if we input it to logistic regressor, we will get some z value, which might be between 0 and 1. This is some notations are wrong. So y is either 0 and 1, and z would be some floating values from 0 to 1, and we will make it into either 0 and 1 by thresholding z value, right? Okay. Anyway, for x whose ground truth is 0, we have to make z value close to 0, right? And for sample x whose ground truth y is 1, we have to make z value close to 1, right? And actually this function, this loss function is enforcing our output z close to 1 if the ground truth is 1, right? And also this loss function is making our output z close to 0 when the ground truth is 0, right? I already told this how this loss function is making that, okay? Anyway, so I will skip this part. Okay, so that's for binary classification task, right? And we will do the multi-class classification task. We will actually extend this binary cross entropy loss towards the multi-class case. And also, we also have to manipulate the output layers, okay? So in binary classification, we use this sigmoid function, right? Okay. We want to bound our final output of the logistic regressor between 0 and 1, and we will threshold it, okay? Because there are only 2 classes, we can do that. But if the output, if we have more than 2 classes, we cannot do that, actually. But instead, we hope to have some n-dimensional vector that represent n classes probability. Okay, so actually, let's say this is n-dimensional vector, and its entry is denoting the probability for class n. Okay, right? So we are inputting some image as input, right? And this might have some cat or dog or some other classes, and there are n number of classes, and this image may have one of them, right? Our purpose when doing this multi-class classification is to revealing this image's class among these n classes, right? So our output should have some probability for this n class, right? Are you following me? Okay. So in this case, for multi-class classification task, our final output should be some probability vector, okay? So one requirement is our final output vector should be probability, so their sum of each entry should go to 1, right? If it is probability vector, then their entries sum should be 1, right? And also each entry needs to be larger than or equal to 0, right? If it is the probability, then it should meet these 2 conditions, right? But in the middle of the CNN networks, composed of some convolution operation and pooling and nonlinear activations, we cannot guarantee their outputs. This input is image, and we apply some conv operation, pooling, and some activations and other operations in the middle. We cannot guarantee this final vector we obtain is meeting this condition. We cannot guarantee that, right? So that's why we need the softmax layers at the end of the network, okay? And what this softmax layer is doing is, we will first apply this exponential function to the final signals we obtained from previous layers, right? You can think this yi is some i's dimensional value obtained from previous layers, right? We will first apply some exponential function to this yi first, and then normalize it by the sum of their, let's say, this is some y vector, and each entry is yi, right? We can think like that. So this y is denoting some vector we obtain after some CNN operations, right? And this notation is meaning if we we will apply exponential function to each entry of this last vector, and then if we sum them, that is this, right? Okay, and this should be, by the first condition, this should become 1 to make this each entry as the probability, right? So that's why we divide it by their sum, okay? And to meet the second condition, saying that each entry should be larger than 0, larger than or equal to 0. So that's why we apply the exponential function, okay? When we apply the exponential functions looks like this. So their y range is anyway larger than 0, right? So we want to transform the last vector of the CNN to have positive values, and at the same time, their sum of each entry to be 1 by applying, first apply exponential function to each entry and normalizing it by their sums, okay? So this is the softmax layer, right? So everyone is following me? Okay. And then by applying the softmax layer, we can secure the last vector anyway have some characteristics of the probability, right? But because if these layers are not properly setted, this probability would not be working, okay? So we have to have proper loss function to train these middle layers, right? And actually, the loss function we need to train this kind of classification network is cross-entropy loss, okay? So previously in binary classification task, we required binary cross-entropy loss, right? In that loss, we consider only 2 classes are there, right? Y1 is either 0 or 1 in that case. But in this cross-entropy loss, this P is the ground truth vector, and denoting, let's say there are n classes, then this P looks like this. The P is n-dimensional vector and having all 0 except for the ground truth class. Okay, this is the ground truth vector P, right? And Q is our output. Okay, our output after the softmax layer. Okay, so this Q of X is having values some positive value. It has some positive value, and it is n-dimensional vector, and their sum should be 1. Okay. We meet this condition because we applied softmax layer on the last part of the CNN, right? And you can think this as the extension of this binary cross entropy laws. It has only 2 classes, right? But you can think this as the extension towards the actually they have same format for each class entry, right? But actually it have n classes here. So by extending the binary cross entropy laws, their form to the n-dimensional class, we can obtain this kind of cross entropy laws. Okay. And actually, because it is composed of the log function, we can divide it into 2 terms to interpret what exactly it is doing. Okay. And the first term is constant because P of X is the ground truth for each sample. So P is kind of constant. It is not variable, right? So this is fixed, having the fixed value, right? So we can forget about this. And minimizing these cross entropy laws is actually equivalent to minimizing this term. And actually, in information theory, this term is called as KL divergence, right? And P of X is again the constant. So to minimize this term, we have to minimize this term, right? And actually this so Q of X is our output, final output, right? And P of X is our ground truth. So by minimizing these cross entropy laws, we can enforce our prediction Q close to our ground truth P. Okay. Okay. So it's the same conclusion anyway. So for multi-class classification task, we are using these cross entropy laws. Okay, instead of the MSE or binary cross entropy we learned. Okay, and in the Pytorch code, there are already defined these cross entropy laws. Okay, and we can just use it. But one important thing you have to be careful is this target is meaning the ground truth, and input is our prediction. In this location, we have to locate our prediction, and target is some constant, which means ground truth. Okay, but one thing is this target should be its value, not this target is not represented as some one-hot encoding vector. I already explained, right? But some of this, it is consists of this kind of integer value denoting the class itself, right? This is one thing you have to be careful about when using these cross entropy laws, right? Because I explained that this was the cross entropy laws, right? And mentioned that this is some one-hot encoded vector, right? And this is some vector having floating value, right? But I mean, if you print out this target, it does not look like this, right? when I mean, this is actually meaning that the ground truth is third class, right? But you have to directly specify it in this target value like that, okay? Like this. That's the thing you have to be careful about when using these cross-entropy loads. But your output is in this format, right? 이거 전달이 잘 됐나요, 이거? 잘 모르겠어요, 제가. 그러니까 P of X가 원핫 인코디드 벡터라고 했잖아요. n 디멘전인데 이게 클래스가 0부터 시작한다 그러면 클래스가 얘 클래스는 지금 현재 2인 거잖아요. 이렇게 원핫 인코딩이 돼 있으면. 그죠? 근데 이거 코드에서 쓸 때 이렇게 쓰면 안 된다고. 그러니까 인풋은 이런 형식으로 써주거든요. 인풋은 실제 n 디멘전 벡터가 나온 거를 그대로 써줘요. 그 확률값을 이렇게 그대로 써주잖아요. 뭔가 이거 확률값이 아닌데 그냥 가비지 값을 넣어서 그런 거긴 한데 뭔가 이 5차원의 벡터를 그냥 넣어주는데 인풋에 해당하는 밸류는 네트워크가 추정한 5개 클래스만 있으면 5차원의 벡터를 여기다 넣어줄 거잖아요. 그게 네트워크에서 나온 프리딕션 값이니까. 타겟을 원핫 인코디드로 넣어주지 않는다. 정답을 원핫 인코디드로 넣어주면 00100로 넣어줘야겠죠. 세 번째 클래스면. 그게 아니고 2로 넣어줘야 된다고요. 이렇게 인티저 값으로 그냥 바로 넣어줘야 된다. 그죠? 그러니까 이게 뭐 유클리디안 로스면은 똑같아야 되는데 인풋과 타겟이 크로스 엔트로피에는 그렇지 않다. 이거 쓸 때 조심하셔야 돼요. 이거 안 그러면 착각하면 오류 납니다. 네. 다 이해됐나요? Foreign students, are you understanding this? Okay. 그리고 next, I will show you the examples of implementing this CNN for multi-class classification task. Okay, and this LUNET architecture is a famous architecture used for classifying some text or some digit. Okay, used by this Yang Kun in 1998. And at that time, the input size was quite small, 32 by 32 or 28 by 28 dimensional images were used, and they are in grayscale image, okay, just having just one channel, right? And we want to estimate the digit. Actually, this is not A. They are having the images denoting 0 to 9 inside. And we want to estimate their digit in the image, right? If this is image input, then we have to estimate is 0, right? And if this is the image, we have to estimate 9 at the end of the network, okay? This is something we want to do. And actually, this is the classification task, okay? And so this is the code for implementing this LUNET architecture. Their training code looks like this. And yeah, anyway, if you want to use Pytorch library, you have to import these two lines of the code, okay? You don't have to have the second line, but it makes you more easier, okay, to implement. And also this is also, yeah, to reduce the code, okay. Anyway, this part you have to import some library, and this part you define some variable, right? Okay. Because we are using 10 class, n classes, it has the 10, and image size, we will use 32 by 32 sized image, and we will use 100 epoch. We will use batch size as the 32, okay? and we will use learning rate as 0.001. Okay, that's some hyperparameters. And this is our LUNET architecture, and we have to define some class whose name is LUNET5. And inside the constructor, we have to define how each layers are, how the networks are designed, okay? And we have actually two middle scale network. The first part is composed of the convolutional layers, pooling layers, and nonlinear layers, okay? Actually, this first part is processing 2D signals, okay? And the last part is applied after flattening the signal to 1D vector, okay? So it is composed of the linear operator, okay? So are you guys understanding this architecture, right? Okay. And this part, you have to define the forward function when image X is inserted, you have to first extract features using convolutional layers and then flatten it to 1D vector and apply the classifier layers and return the final, here 10-dimensional vector, meaning the probability for these digits, okay? Okay. So here n underbar classes, that's the final dimension. And actually, yeah, here it was defined to be 10, okay? Okay. And the next thing you have to define is how to load the data. Actually, in previous slide, I taught you here, one part is missing, okay? Actually, I mentioned this X and Y are input X and ground truth Y, right? But how to load them was missing, right? That is actually will be explained here. Okay. So you can read yourself, right? But if you use this data loader, it provides some easy interface. Okay. So actually, this is also provided by Pytorch library. Okay. So the first thing you have to do is you have to define the data set. Okay. You have to define the data set. Okay. And if you, so our data set is defined here, this line of the code. And if you insert this data set defined here in the data loader, this data loader is providing some more functions, easy functions to you, such as you can adjust the batch size of it easily by only by changing here the value here, right? Right. So for the students who are not familiar with this batch size, so I will explain the batch size. So batch size is the number of images which are parallelly processed during training or testing. Okay. We are not processing just one image during training or testing, but we can parallelly use multiple images for training and testing, right? And this batch size is meaning how many images we will use parallelly, right? Okay, so it is kind of tedious job if you manage it by yourself, right? You have to concat image vectors or you have to concat ground truth vectors by yourself. to manage this batch-wise processing, right? But if you use data loader, if you specify only the batch size here, then data loader automatically loads the images using this number of images. Okay, it's quite easy interface, right? So please use this data loader. And also the shuffling is also not that great thing. I mean, I will also explain why shuffling is required first. During the training, if you shuffle the number of orders, orders of the images used for the training becomes more robust by preventing some overfitting phenomena, right? Using some randomness during the training, you can make the model more robust, right? So that's why we use shuffling during the training, okay? And if you use true flag to this shuffle variable, you can, anyways, easily shuffle the data, image data during the training, right? But the test loader, we will not use the shuffling because during the testing, we do testing for measuring our model's performance usually, right? So let's say there are 100 images and we have to measure the accuracy of our model by evaluating our model on that 100 images, right? And that accuracy actually does not change if we see the images from in this order. This is image index, right? So if we see the image from whose index is 1, 2, 3, 4, 5 to 100, the accuracy would be like 50%, let's say. Then if we shuffle it like this, and check the accuracy, it would be saying me 50%, right? 이거 이해되나요? 자, 테스팅에서 셔플 해도 accuracy는 똑같잖아요. 100장 있으면 1번부터 100번까지 순서대로 재도 150%고 셔플링 하고 2번 재고, 1번 재고, 4번 재고, 5번 재는 순서대로 재도 50%죠. accuracy가. 그러니까 accuracy 재는 게 테스팅의 목표잖아요. 그러니까 굳이 셔플링 할 필요 없는 거죠. Okay. So the accuracies are same regardless of the orders of the images during testing, right? That's why we are not doing any shuffling during the testing. We can do that, but there's no merit, right? But during training, if we do shuffling, we can make more robust models, right? Involving some randomness, right? Okay. Anyway, also we can use some data parallelizing. There are some options for that. If you search for the data loader and see their options, then there are also the options for that. Okay, reading multiple, using multiple cores for loading the data. Okay, you can use that as well, right? So anyway, Pytorch is providing some easy interface for helping us loading the data. Okay, that's why this data loader was used. Okay, but first thing is we have to define this data set. Okay, after defining this data set, we can use data loader. Okay, but data loader is providing this kind of property. And actually, for defining the data set, there are two ways. Okay, the first one is easier, but not easy to generalize to a new data set. I mean, there are actually frequently used data sets such as MNIST or other kind of CIFA 100 ImageNet like that, right? Those data sets are frequently used data set, okay, popularly used data set, right? And Pytorch they are implementing some code for loading those kind of frequently used data sets here, right? They are providing some easy interface for defining such a frequently used data set. If you go to this link, then you can see some grammar for that. And actually, we are using that for this MNIST, for defining this MNIST data set, right? Inside these data sets, there are many data sets already registered in the Pytorch library. And dataset.mnist, by using this grammar, we can easily define the MNIST data set. Okay. Okay. And also, if you check this as true, then if the data set is not in your hard drive, you can even download it when you first execute this code. Okay. Anyway, and also you can apply some transformation function like flipping or resizing the images by defining some transformation functions here, right? So anyway, if you use this data set format or this data loader, loading data is a lot easier, okay, by implementing it from the scratch, right? But if you use this kind of predefined function for defining the data set, you cannot load the new data set. Okay, maybe sometimes you want to collect some data and want to involve it during the training, right? Not using some popular data sets. Instead of using the popular data set, you want to collect your own data set and want to use it during the training, right? In that case, you have to define data set like this, okay? You have to import these two packages and have to define the dataset class, okay? And it has to have these three methods in it, okay? And actually, this len is denoting the number of data inside this dataset, okay? This is denoting number of data. You have to return the number of data in this len method, okay? Network structure as well. It is once executed when instances are made, right? And normally you directly create data here, directly define X data and Y data here like this. Or if the data set is large in scale, you can only specify some paths for the X data and Y data, right? Okay. Anyways, this init function, you have to specify how these X and Y data are located, okay? Or you can define the values themselves here. And this get item method, you have to define how your data are loaded, okay? So because here, this self.x data and self.y data are already defined, the only thing you have to do here is by changing their types to floating value and return this x and y, okay? So you have to define how one samples are returned, or I mean formatted. So one sample here, they are having X and Y pairs, right? So and you will return it by this format, X first and Y next, okay? Or you can implement it like Y comma X like this, right? Anyway, when you read the data, your data are read in this order. I mean, the order you implemented here, the data are loaded, okay? So this get item method, you have to define how you load one sample, okay? So actually, this is another way to define data set. This is one way of defining the data set using some Pytorch zoo, saving the frequently used data sets. The other way is defining the data set by yourself, okay? Maybe you have to use it for project and the homework, right? Anyway, and the next thing I have to explain is stochastic gradient descent, okay? Actually, the Pytorch, when we define the optimizer, we use this function, right? Even when implementing the gradient descent, we use this function, right? Because the stochastic gradient and gradient descent, those are actually same for their operation. Their formula, they are samely does this kind of operation. Okay. They update the parameters towards the direction of DLD setup, right? Towards the direction of reducing the loss function, right? This is same for stochastic gradient descent and gradient descent, but their difference is for gradient descent, we update the parameters after seeing all the data. If we update the parameter after seeing all the data, then it's gradient descent. But if we update our parameters after see only the partial data, that is called as stochastic gradient descent. Okay. Their operations are same, but how many samples they see before parameter update, yeah, these two things are differently defined. Okay. Maybe some of you think that gradient descent is better than the stochastic gradient descent, but in practice, SGD performs better than gradient descent, right? Because we are training our model on training data, which is different from the testing data, okay? Our aim is to make our model works good at the testing data, right? But we are applying this gradient descent and either of these gradient descent or stochastic gradient descent on the training data, right? Okay, so making our optimizer become optimal for training data does not always mean that our model is working best for the testing data, okay? So if we use gradient descent, we will see all training data, okay? We optimize our model once after seeing the training data, all of the training data, okay? So it performs one optimal update, right? But stochastic gradient descent, it update the model after seeing partial training data. So we can think it goes non-globally optimal steps, right? But sometimes it is helpful to involve some noise during the training to preventing the overfitting phenomenon, right? So, I mean, stochastic gradient descent is, in practice, works better than gradient descent because it involves some randomness, okay? So gradient descent, it updates the model after seeing all the data. Globally, it goes some global optimal step. However, stochastic gradient descent, it only see this partial data and update model after seeing this partial data. Okay, so this is the model parameter space. Okay, and our weights, the model parameter, are update like this. This is, let's say, the optimal parameter for the training data, right? And stochastic gradient descent, it updates in a kind of stochastic way. It looks unstable, right? But in practice, it can lead our model works better than testing data. So this point is optimal point for training data, right? But not for testing, okay? And this is not definitely the optimal point for the training data, right? But could be better point for the testing data, okay? So are you understanding this? Okay. So, but I mean, if the data size is small in scale, I mean, if we are just having 100 data or 30 number of data point, let's say, then, and also our batch size is 32, let's say, then gradient descent is actually same as the stochastic gradient descent, right? But the difference between these two is maximized when the data size is large, right? Actually, when the data set size is large in scale, for example, if we have 1 million data samples, updating our model after seeing 1 million data, that's not that good for the testing data. That's what I'm saying, okay? Instead of that, we may have to update our model after seeing only 32 images, okay? That would be the okay. And when implementing this LUNET, because we are having, as far as I remember, this number of data points, so we will use stochastic gradient descent. But in previous implementation, for example, when training the linear regressor, we made by ourselves, made this 100 samples, right? Here our code style was update our model after seeing all the data. So even though we are using stochastic gradient descent as our optimizer, here we defined it as stochastic gradient descent, but the code style we implemented was actually the gradient descent, okay? We update our model once after seeing all the 100 data, right? But here, because we are having 60,000, we are having this number of data. it would be inefficient if we update our model once after seeing this number of data, right? So we will update our model after seeing the batch amount of images. Okay. 이거 이해되나요? So when you see the code, you can feel that our implementation is based on the batch. Okay. So I will first implement the training code. Okay. And as the argument, I have to get this amount of input. The first input will read the data X and Y for you, okay? And the second argument, it will get the model, the CNN model we will train. And third argument, that is the loss function. And fourth is the optimizer, okay? And you don't have to forget this line of the code. You have to set it as the training mode, but for the testing mode, you have to do this kind of, you have to do right this line of the code, right? And this is for setting some variable and initializing some variable. And here, if you specify your data loader here, then the data is loaded in the order you define here, okay? So in the for loop, you can directly specify your data loader like this. Then your data are loaded in the format you defined in your dataset definition, okay? And anyway, the dataset would be loaded from the data loader, and actually it will be loaded with some batch size, okay? And you will see the same 5 lines of code for updating the model like this. So first you have to initialize the gradient value as 0, and you have to do forward function, right? And calculate the loss, right? And I mean, this is for calculating the accuracy and storing the losses, okay? So this is for visualization, not very important. But the important thing is applying this loss step backward and optimizer step to update the parameters, right? In the for loop here, for samples loaded from the data loader, you will update your model, right? So actually we load the data here for one batches, and one batches, in the hyperparameter in previous slide, we specified that there are 32 images, right? So after seeing 32 images in a batch, we will update our model once after seeing the one batch. So this is, I mean, the batch-wise update, okay? The stochastic gradient descent, okay? And this is for calculating the accuracy and so on, okay? So this is training code for one batch, okay? So now we implement the training code for one batch, and this is the code for testing for a batch. The difference is we don't involve this part. We don't involve. We do forward pass, but we do not do something related to the backward things, okay? So there's no gradient initialization and there's no backward, except that the testing code for a batch is same as the training code for a batch, okay? You can just remove this backward related thing, okay? And this is the code for training for whole data, okay? Previously, it was training code for one batch, right? But here, it is code for training for whole data, okay? And this is the loss, the initialization for the array, wanting to store some losses. And this is the iteration for whole data. So how much this epoch means, if you see whole data once, that's one epoch. Epoch means the unit for seeing whole data, okay? If you say you train the model 10 epochs, then it means you saw whole data 10 times during the training, okay? So epoch is defined like that. So this is loop for how much you see the whole data, right? And sorry, I mean, I think I misunderstood this code, sorry. This code is for not one batch. This is the training code for one whole data. Sorry about that. So using this train, you can read whole data in the data loader by batch size, okay? Sorry about that. This for loop will read whole data. So this for loop exited when you see whole data, and for each round of this for loop, it processes the batch size amount of the data, okay? And you update it after seeing that amount of data actually, but by involving this for loop, you will see whole data, okay? So this code is for training code for one whole data. And here, we specify how much we will run this train function, which sees one whole data, okay? Sorry about that. And after once executing the code for one whole data, you will evaluate your model using this test function that also sees one whole data, one whole test data to evaluate your model, right? But for the evaluation mode, there would be no gradient calculation. So you can specify this kind of option with torch.no gradient. If you specify this, the code execution time is reduced actually, okay? Because it does not involve any gradient calculation. Inside the Pytorch, you don't have to calculate some graph construction, okay? So this will accelerate the code speed, okay? And after that, some visualization is done, okay? So training on the loop, this is the training for whole data for several epochs, okay? And in the top level, you define the loss function and optimizer, and also define the model and execute this training on the loop, okay? That manages the whole training, okay? So this is the code for actually does both training and testing using the CNN architecture. for multi-class classification. Okay. But if you do execute this code, then this code does not involve any GPU calculation. Okay. So each line of the output that is denoting one, the result, the train loss, test loss, train accuracy, test accuracy after each epoch, right? So the train loss gradually reduced, test loss gradually reduced, training accuracy gradually go up, testing accuracy gradually goes up, but it may take a lot of time to execute this code, okay? Few minutes for executing this 15 epochs, right? If you involve more data and more complex network, this training time takes more, right? You may wanting to speed up the training time, okay? So anyway, this is using only CPU, but in the collab or in your local machine, you want to use some graphic processing unit, the GPU, okay? And collab, you can do this kind of thing to use the GPUs, right? Okay. So this is actually denoting the flag, denoting your GPU is available or not. And if you do not, if you print out this value before setting the GPU, that would be set to false, right? But if you do this and execute that again, the availability that becomes true, right? So after seeing back this true value, you can use the GPUs inside the collab, okay? And the code also have to be changed to use the GPUs in your code, okay? I will explain from here to the previous slide. So this line of code is, if this value is true, then you will use CUDA for device. This is meaning GPU mode. Or this is false, then you will use the CPU mode, okay? You have to copy your model and data into GPU if you want to use the GPU mode, okay? So first, by using this code, you can copy your model into the GPU, okay? And then we will also copy the data to the GPU. And so that purpose, we first input this device variable inside as the argument for this training loop. And also we transmit it in this train and test functions. And then we have to copy our X and Y data to our device, GPU device here, right? And training code, we also have to copy our data into GPU, okay? So this is the way to use GPUs in our code, okay? So we first set our GPU. In local machine, we have to set some CUDA library, okay? Properly set our GPUs by installing CUDA, okay? Then we have to set our device as CUDA and also have to copy our model and data into GPUs, okay? After doing that, it takes 1 or 2 minutes for these 15 epochs for processing these 15 epochs. So a lot faster, become a lot faster, okay? And I will, after this, review some famous CNN architectures such as AlexNet, BridgeNet, and GoogleNet, and ResNet. And we'll go into explaining about the object detection model, okay? So yeah, I think we can finish here for today's lecture, okay? If you have any questions, please comment and ask me, okay? Thank you.